Okay, it's Brian, and I'm here to talk about the solutions for day 4. And those were problems that had to do with chapters 14 through 16. That was the oscillations and waves section of the course. And we're starting with a problem having to do with kangaroos. Okay, so we've got a 70 kilogram kangaroo who hits the ground, tends to stretch to maximum length, and the rebound causes the kangaroo to leave the ground approximately 0.1 seconds after its feet first touch. And the motion of the kangaroo as it's bounding across the landscape has two different phases. It's got the time when the feet are in contact with the ground. We call that the bounce. And then it's got the time when the kangaroo is flying through the air, and we call that the flight. Okay? Now, during the bounce and during the flight, we're assuming that the horizontal speed is constant. Okay? So we're just going to focus on the vertical speed, and it alternates between periods of positive motion and negative motion, moving downward. Okay? Now let's think about the questions first. And there's no rule that we have to, but I think in this case it makes some sense. So question 1, we're going to model the motion of the kangaroo when it's in contact with the ground as the motion of a mass on a spring. Question, what is the period? Well, let's draw a picture, a graph as it were, of the y position of the kangaroo as a function of time. So when it first hits the ground, okay, the kangaroo is moving downward, and so it's going to go down, and then at some point it reaches its lowest point, and then it reverses direction and comes back, reaches the same height as when it first hit the ground, and then it's leaving the ground. Now, if we think about this as the motion of mass on a spring, that's only 1/2 of a cycle. A full cycle would be a positive and a negative portion of the wave. So it looks like this period of time when the kangaroo is in contact with the ground, which is 0.1 seconds, is really only half of a complete cycle of oscillation. So the period is going to be double 0.1 seconds or 0.2 seconds. Okay? Now let's think about this. Next problem. Okay, if the kangaroo speeds up, it must bounce higher and farther with each stride, and so must store more energy in each bounce. How does this affect the time of the bounce and the time of the flight? Well, the time of the bounce, if it's motion of mass on a spring, let's think about this. We drew a thing which looked like this. And then if the kangaroo hits going faster, it's just going to have a bigger amplitude, but the time will be the same. And if it's even faster, it's going to have the same time, but it'll have a different amplitude. That's what a property of the mass on a spring. The frequency and the period are fixed by the spring constant, i.e. how stretchy are the tendons, and the mass, i.e. how heavy is the kangaroo. And then, if the kangaroo leaves the ground at a certain speed, it's going to follow a trajectory through the air. If it leaves the ground going faster, it's going to go farther. If it leaves the ground going even faster, it's going to go even farther. So if it hits the ground with more energy, the time of the bounce is going to stay the same, but the time of the flight will increase. And so it sounds like our correct answer for this one is B. Now for the problem, we're supposed to draw a graph. And we're told to assume that the bounce lasts 0.1 seconds and the flight lasts 0.3 seconds. We're supposed to sketch a graph of the vertical velocity as a function of time. Okay, so let's do this. I'm going to go ahead and first just sketch out my axes. So I'm going to do the vertical velocity as a function of time. So here's my Vy as a function of time. And I'm going to put some times on the axis. Okay, 0.1 seconds, 0.2 seconds, 0.3 seconds, and 0.4 seconds. And let's assume that the kangaroo starts with the bounce. So it hits the ground, moving downward, hits the ground. What happens subsequently? Okay, now the bounce phase is this first 0.1 seconds. Okay, so this first phase of the motion is the bounce. It hits the ground when it's moving downward, so the initial velocity is 0. When it leaves the ground, it's moving upward. And looking at our picture right here, thinking about this as simple harmonic motion, it's symmetric, so it should leave the ground at the same speed that it hit the ground at. So the distance of this thing above the axis should be equal to the distance of this one below the axis. Between there, it's motion with simple harmonic motion, and if I sketch half of a sine wave between those 2 points, it's going to look something like that. But now the next 0.3 seconds are the flight through the air. Well, for the flight through the air, it's parabolic motion, it's projectile motion. We know how that works. The vertical speed changes because it's free fall. And so you're going to get a linear decrease in the vertical velocity. It's going to look something like this. And the slope of that graph is going to be 9.8 meters per second squared, negative. That's just equal to the acceleration of free fall. So we're going to get something like that. And then when it reaches the ground, it's basically comes back here. You're ready for another cycle, ready for another bounce. Okay? And so that's what it's going to look like. And the question asks us to pay close attention to the shape of the segments of the graph. And if we were grading this and you had solved this, we would be looking for that. This piece should be half of a sine wave. This piece should be a straight line. This piece is 1/10 of a second. This piece is 3/10 of a second. That's what we're looking for the motion of the kangaroo. Let's take a look at our next problem. Now this is another oscillation problem, and it's asking about jellyfish. And jellyfish propel themselves by pushing water out of their bell, and that's a flexible structure on top of their body. And it turns out the bells are elastic, and the motion of the water in and out of the bell is kind of like mass on a spring motion. And if you look at this graph right here of the deflection of a point on the bell as a function of time, you can see it looks like mass on a spring motion. It looks like a sine wave. The only thing is it's damped. Instead of continuing with the same amplitude, it kind of like decreases amplitude. But basically it's mass on a spring motion. Okay? And so we're basically solving a problem of simple harmonic motion. This is just simple harmonic motion in a jellyfish. Now let's take a look at this graph. And the first question asks us this. The displacement is 0 at 0 seconds. What is the earliest time at which the speed is 0? Well, if I have a graph of position, which deflection is a position, as a function of time, the velocity is the slope. And the first point, where the slope is 0, is going to be at this point right here. That is at 0.25 seconds, which is what this point is right here. So it's 0.25 seconds, 1/4 of a second. The velocity is 0. So the first question, the answer is C. Okay? Actually, it should be B. I don't know why. Like this was, in the document you have, it was A, B, C, D. For some reason, on the one I uploaded is A, B, C, D, E, whatever. Anyway, it's this one. It's 0.25 seconds. Next question asks, what is the approximate period of the motion? Well, remember, the period is the time for one cycle. And I'm going to go back and I'm going to take a look at my graph, and I'm going to look at the time between successive peaks of the graph. Let's look at this one and this one. And the time between those 2 points is 0.75 seconds, 3/4 of a second. And that's also the time between this peak and the second peak. This is also 0.75 seconds. So it's a pretty clear indication that the period of the motion is 0.75 seconds. Now with that information in hand, we can solve the problem. We're asked to figure out the mass of the water in motion, and then 2, the maximum speed of the motion. Now we're modeling this as simple harmonic motion, and the frequency of simple harmonic motion of a mass on a spring is 1/2 pi times the square root of k over m. In the problem statement, we're told that the spring constant is 1.2 Newton meters. Okay, I'm sorry, newtons per meter. The frequency is just 1 over the period. Well, 1 over the period is 1 over 0.75 seconds. And so we know what that is. The only thing we don't know in this expression is the mass. We can solve for it. And when I did, I got a mass of 17 grams. And that seems reasonable. This is a small jellyfish, and we can tell that by the spring constant. That's a very, very gentle spring constant. And we know this has got to be a small jellyfish for this to be happening. And the mass, I get, say, 17 grams. And it's a tiny, I expect it to be a tiny mass, and it is. Next piece of the puzzle, what is the maximum speed of the motion? Well, remember, for simple harmonic motion, the maximum speed was equal to 2 pi times the frequency times the amplitude. And if I want the maximum speed, I want the maximum amplitude. And the amplitude is just the maximum value of the deflection. So for the amplitude, I'm going to take it to be 0.6 centimeters, or 0.06 meters per second. That's the amplitude. The frequency was 1 over 0.75 seconds. 1 over the period. Oh, and with everything in hand, I can calculate the maximum speed. And if I do that, I get a maximum speed of 0.049 meters per second. And that's a pretty relaxed velocity. That's pretty slow. That's 4.9 centimeters per second. And we expect it to be a small mass and a pretty slow speed. This is, jellyfish are not speed demons. This is whatever the jellyfish is doing, it's not doing it quickly. So this makes sense. Next piece, I have a problem about Milo, and it is absolutely true that Milo's hearing is way better than mine. His threshold of hearing is about -10 decibels. That's typical for a dog. My threshold of hearing, of course, is 0 decibels. And so the question is this: if Milo and I are out and I can just hear a mouse, it's the limit of my ability to hear it, i.e. it's at 0 decibels. Milo can hear it at 10 decibels. He can be farther away. If I'm at a distance of 1.5 meters from the mouse, how far is Milo from the mouse is ultimately what we're looking at. Well, 2 questions to ask first. First off, what is the intensity of the quietest sound a human can hear? That is, by definition, I0 is equal to 1.0 times 10 to the negative 12th watts per square meter. That was something we were given as a definition. When we define the decibel scale, we use that number I0. That's the quietest intensity humans are generally capable of sensing. It was 1 times 10 to the negative 12th watts per square meter. So that's that number. What is the intensity of the quietest sound a dog can hear? Well, if I'm given a value in decibels, remember the intensity that corresponded to it was I0 times 10 to the power of the sound intensity level divided by 10 decibels. Well, the intensity 0 is 1 times 10 to the negative 12th watts per square meter. We just said that. And then that's times 10 to the negative 10 decibels over 10 decibels, which is just -1. So 10 to the negative 12th times 10 to the negative 1, which is 10 to the negative 13th. So it's 1 times 10 to the negative 13th watts per square meter. So for the first question, the answer is definitely 10 to the negative 12th watts per square meter. And for the second one, it is 1 times 10 to the negative 13th watts per square meter. And a sharp-eyed student noticed if this is the smallest intensity a person can hear, we know the dog can hear a smaller intensity. The only answer that satisfies that is D. So I've done a quick assessment even on the multiple choice. Next question, how far is Milo from the mouse? The way I'm going to solve it is to say the mouse is here and the sound spreads out as spherical waves. And I'm right here. I can just barely hear it. So at my position, the intensity is equal to 1 times 10 to the negative 12th watts per square meter. Well, that's equal to the power of the source divided by 4 pi r squared, where r is the distance from the source of sound. So we can figure out the power of the source, which is the mouse. Okay, so 1 times 10 to the negative 12th watts per square meter is my intensity. Over here, r is equal to 1.5 meters. That is how far I am from the mouse. The only thing I don't know in this equation is the power of the source. And if I use this equation to solve for it, I get the power of the source is equal to 2.8 times 10 to the negative 11th watts. And that makes sense. That's a really, really tiny power, and we expect that because it's a very small intensity. Milo, on the other hand, can be farther away, and the question is we have to figure out how far away Milo is. Same power, same source, spreads out like so, and I'm going to try to draw a picture of Milo. There's his ears, there's his body, there's his tail. Okay, so there's Milo, and he is a distance, I'm going to call it r, from the mouse, and I know it's farther than my 1.5 meters. The intensity he can hear is equal to the power of the source divided by 4 pi r squared. Well, I know the power of the source. That's just equal to the 2.8 times 10 to the negative 11th watts. I know the intensity that Milo can hear. That's 1 times 10 to the negative 13th watts per square meter. The only thing I don't know in this equation is r. I can solve for it, and if I do that, I get a distance of 4.7 meters. Here's a quick assessment. Milo can hear an intensity that is 1/10 a the intensity that I can sense. And the intensity is proportional to 1 over r squared. Now, if I increase the distance by a factor of 3, I decrease the intensity by a factor of 1 over 3 squared, which is 9. And 1/9 is approximately equal to 1/10. And so I'm expecting the distance to be bigger by about a factor of 3. I can hear it at 1.5 meters. Milo should be able to hear it at 4.5 meters or 4.7 meters. That makes sense because 1/9 is slightly less than 1/10. And so my answer of 4.7 meters makes sense. Next problem has to do with heating tissue. And this is using an ultrasound source to heat tissue below a person's skin. So the situation is working like this. Okay, so here's the top surface of a person's skin. Here is bone beneath the skin. There's some sort of an emitter which is placed, an ultrasonic emitter which is placed here at the surface of the skin. And it's emitting waves, and the waves go down and the waves come back because they bounce off the bone. And when they do that, I can have the conditions for setting up a standing wave. Now we're told that where the emitter touches the skin, the amplitude is quite large. So what it's telling me is this position right here is an antinode. We're also told that where there's the boundary between the tissue and bone, the energy is reflected, the amplitude is small. That means right at the bone, I'm going to be having a node. So I have an antinode at the surface. I have a node down below. And so I'm going to get standing wave patterns that look like this. I can have an antinode at the top, a node at the bottom. That's an option. I can have this mode right here, or I can have antinode at the top, node at the bottom, and I can have this one. And so on and so on. These are the modes for a open, closed system. So we're going to assume that the modes are similar to the modes of an open, closed system. And for that case, the frequency of the mth mode is equal to m times v over 4L. And I've jumped ahead, but I was just excited about standing wave modes, and so I kind of had to do it. Now let's go back and do some calculations for the questions. First thing, what is the approximate wavelength of the microwaves in tissue? Well, it's always true that v is equal to f times lambda, and so therefore lambda is equal to v over f. V is the velocity of sound in tissue, and you can look up at a table in the book. That's 1,540 meters per second. And if you needed that on a test, of course, I would give that number to you. The frequency is 0.75 megahertz, so 0.75 times 10 to the 6th hertz. And if I calculate what the wavelength is, I get that the wavelength is about 2 millimeters. Okay, so it gets about 2 millimeters. Next question. Longer wavelengths have greater penetration than shorter wavelengths. If I want to increase penetration, I need to have an increased wavelength. Well, if the wavelength is going to go up, so it's v is equal to f times lambda, if the wavelength is going to increase, the frequency has to decrease. And so the answer for that one is B as well. I need to decrease the frequency to make this work. Then for the problem, we've already written down an expression for what the frequency of the mth mode will be. It's just m times v over 4L. V is equal to the speed of the ultrasound in tissue. That's 1,540 meters per second. And the question asks for what depths would standing waves be created. The frequency is 0.75 times 10 to the 6th hertz. For different values of m, I can get different values of L. And if I do that, I'm just going to take this equation and rewrite it in terms of L. And if I do that, I get that the lengths that I'm looking for are just equal to m times v over 4f. And I know what v is, and I know what f is. And if I calculate values for the distance below the surface, because remember L is basically the length of the system, I get distances of 0.51 millimeters. I get 1.53 millimeters. I get 2.55 millimeters, and so on. And those are small depths, but frequently if you're using ultrasound on tissue over top of bone, it's not going to be very far below the surface. Those are kind of like reasonable depths where you might expect to see that kind of transition. And you could get staining waves. And if you get staining waves, it's not always a good thing because you can have really hot spots, and that could be uncomfortable. And that is the end of this problem set.